It's 1 p.m. on the dot. We, of course, have a very packed agenda. So first of all, welcome everybody. We are very pleased that you chose to spend your time with us instead of hanging out outside with the nice weather. So we do appreciate it, and I'm sure you'll have nice and useful time. So this tutorial will be about using OHDSI vocabularies for research. And we have an absolutely amazing faculty. I myself work at Johnson & Johnson, and I'm also an adjunct assistant professor at Columbia University. We also have Aza, who works at Johnson & Johnson, Vlad and Oleg work at Odysseus and EPAM company, and Polina, who works at Cyforce. And all of these people, sure, we can do an applause. And all of these people have years and years of expertise in both ontologies and phenotyping. So we have a perfect crowd to hopefully teach you on how to use vocabularies for research and to have a nice, productive conversation. And we also have wonderful teaching assistants. We have Dima, we have Andy, and we have Alexander, who will help us tremendously in our exercises. And as we said, tutorial is really around using vocabularies for research. So we wanted to select a topic for research to sort of ground ourselves in what we will be doing. I think there are two spots right here for the people who are coming. Wonderful. So we looked at the recent guidelines, and kind of the first guideline I looked at, which was the most recent guideline for management of lupus, from the very start highlighted the gap in the guidelines, which is coming from all of the new drugs coming to the market since 2019. And the guidelines do not really incorporate all of these new drugs because they don't know how they're used, how the patient outcomes look like, and they themselves acknowledge that this is a gap and they need to work on that more. So naturally, that is an opportunity for us not to wait for this evidence to be generated, but generate it ourselves. So what we can do is we can take a look at real-world data and see how patients with lupus are treated and what kind of drugs they're getting. And luckily enough, we in fact have open source tools and packages for you to do that. So here specifically, we have treatment pathways module in Atlas, that very nicely provides you the information. Oh, and here we have our teaching assistant. Andy, please come here. We have a spot for you. So the treatment pathways provide you very nice graph showing the patterns of the treatment and drug use, and it also provides you with the tables outlining how many patients are treated, how many patients are not treated. And this tool is available open source, and we've used that to produce one of the papers by Hripsak et al. Looking at the treatment pathways in diabetes that since 2016 was cited multiple times. So this open source tool does enable you to actually carry out this research and publish a paper. And we also have open source tools for other research questions that you may have, all the way from incidence rates analysis to more complex things like a patient level prediction. And we've used all of these tools successfully to yet again produce impactful papers that then impacted decision making in real care. But for us to use these tools, we first need to pass in the standardized input. And here, being very specific, what we need to standardize is the way we identify patients of interest. And if we talk about treatment pathways for lupus, we first need to find patients with lupus in our data, and we also need to find patients that are taking drugs of interest, like methotrexate and corticosteroids. And for this standardized way of identifying the patients, we in fact also have the pipelines backed up by the open source tools. And in the pipeline that we use in the OHDSI community in our best practices, you start with a clinical description that outlines all of the details about the condition of interest. You also use the prior knowledge from the literature or other sources to learn how these patients were identified in the data before. Then you take all this input and you pass it into these processes in the box in the middle, where we start with creating the concept sets to find our patients of interest. Then we use these concept sets as the building blocks to create our cohort definition, or phenotype and algorithm, or phenotype, there are many words. And the cohort definition is an executable algorithm to find your patients of interest, and it's more than concept sets, because when you're trying to identify a cohort, you're thinking about multiple questions. When does a patient enter the cohort? When do they exit? What kind of inclusion and exclusion criteria you need to apply? For how long these patients need to satisfy these criteria? So the algorithms are more than the concept sets, but the very first step is to come up with these concept sets, and this is what we will mostly talk about in this tutorial. We then take this algorithm, execute it on the data, get a cohort of patients, and evaluate how this algorithm performs. And we have different tools for that to compute performance characteristics, to assess patients. And if you're interested in the rest of the steps, please come to the phenotype work group that will happen on Thursday in the morning. In this session, we will focus on the concept sets. And then at the end, you get naturally the cohort of patients themselves, the algorithm that you can run, and the evaluation reports. And when we talk about concept sets, what we really mean is the list of one or more concepts. And these concepts are the codes that are used in electronic health records, claims, registries. And this is where doctors or medical coders go through the data, look at the patient charts, for example, identify what patients have, and assign codes to them for their procedures or diagnoses. And these codes are coming from structured terminologies, and the terminologies are different depending on what you're looking at. For example, traditionally in the United States, for the data before 2015, we used International Classification of Disease version 9. Then after 2015, we switched to ICD-10. If you were to look at the data, for example, in UK, you will find different vocabularies that are used there and different codes coming from read vocabulary. And there are many more ontologies and vocabularies that are used in different data sources. Even within the US, ICD-10 and ICD-9 are not the only vocabularies for conditions and diagnosis. For example, we have ICD-3 for cancer diagnosis. And the whole totality of these vocabularies and the fact that there are many of them makes standardized analytics really hard, because all of us now are talking different language and we have different codes, we have different names. So it's really hard to do something in a standardized fashion. So that's why we, in OHDSI, we introduce this notion of the common reference standard. And for example, for diagnosis and for conditions, it's SNOMED, where we say that you can speak whatever language you speak, we're going to translate it into the common reference standard. And for all of our standardized analytics, we're going to use these reference standards. So what we do is we create this maps to link, or links of equality, between the codes in all sorts of source data from US, from UK, from Australia, from registries, from claims, doesn't matter, to this common reference standard. And the orange circles, the codes in the source data are becoming non-standard. This is what we call them. And the ones in blue are reference standard, are standards, and this is what we use for research. And luckily enough, these common reference standards also provide us with the hierarchies so that we can easily navigate and get the groups of codes that we want. So SNOMED, for example, is organized in the very nice hierarchy that sits in the OHDSI vocabularies. And we also have some classificational terms to help you even more. And in this tutorial, we will be focusing on these structures and how to use these structures to get the concept sets to identify patients of interest. And in the OHDSI vocabularies, we import all of the vocabularies, we create the links, so all of the concepts can be found in the concept table, all of the relationships among concepts can be found in the concept relationship table, and finally the hierarchy can be found in the concept ancestor table. And these tables can be retrieved and talked to via SQL statements or R statements, but also we will show you user-friendly interface on how to access the very same information in a user-friendly manner. And the tool we will be using for that is Atlas. Now, we only talked about the small portion of vocabularies, but vocabularies now is a beast of all sorts of things from many countries. We have vocabularies for diagnosis codes, for procedures, for drugs, for devices. And now we have more than 8 million concepts in the whole vocabularies and more than 50 million relationships among them. We also have hierarchy with the various degrees of fidelity depending on domain, but that, even looking at this picture, it feels like now it's really hard to navigate this thing because we have so many concepts and so many relationships. That is absolutely true. It may be hard to navigate it. On the other hand, all of this information provides us with a useful source of knowledge that, if used properly, will really help us in our tasks. And when we go to the tasks, to our agenda, we will first cover conditions and measurements, how to create concept sets for conditions and for measurements. We will have demos, we will have exercises, of course we will have discussion. Then we will have a break, and the second part will be focused on drugs and how to create concept sets for drugs. Now with that, I will pause to see if there are any questions. Yeah, go ahead.
My question is about relationships. Go 2 slides back.
Mm-hmm.
Here. Concept relationship. Relationships are the relationships between concepts. Are they only limited to the mapping relationship between non-standard? So there are no other associated relationships included.
So we do import. Thanks so much for the question. So the question was, what kind of relationships we have? So we import all of these vocabularies. So we have all of the relationships coming from vocabularies. And for example, SNOMED had dozens of different relationships. We have them all. And we also built maps to relationships. This is what we built. And then the hierarchies that are in the concept ancestor table, but also the links for us to build the hierarchy are in the concept relationship table. For example, subsumes relationship will be in the concept relationship table that we partially built and we partially imported from the sources. So it's going to be all sorts of things, but for the purpose of this exercise and for most of the users, the thing that we care about is the mappings, and then the hierarchical relationships you will be able to access through the concept ancestor table. Go ahead. Mm-hmm.
How then, is there anything in the concept relationship table which would specify the type of mapping? For example, 1 to 3 and at least 2 must be true, or is there anything beyond a direct map?
Yeah, so that is a wonderful question. The question was, sometimes we have one-to-many mappings when SNOMED does not fully represent the notion of the source concept we are trying to map. A classic example is conditions in pregnancy, where we map to both pregnancy and the conditions. You will be able to, so both of these links are valid. So there is nothing about one of the links that is worse than another. But what we introduced in this very release is the metadata for relationships. And we will talk about that more on the vocabulary work group on Thursday. But there the metadata specifies for some of the mappings, whether these mappings are exact match, uphill match, or downhill match. So please come to the vocabulary work group.
So the middle circle, like the dark circle at the far left side, is standard.
Mm-hmm. Oh, yeah, that was supposed to be standard. Mm-hmm. So orange, what we're going to use throughout is orange non-standard, blue standard, and light blue classificational. Yeah, absolutely. Oh, people are looking at the slides. How nice is that? I thought there were some questions in the back. No? Alrighty. So now we will get into more details and we'll come to the more hands-on part. I am right on time. That is surprising.
Okay. I'm known to be never on time. I mean, I always run out of time. But so if you saw the agenda, we're going to try to do an exercise of how we get to the concept set when we're interested in a condition. So that's a diagnosis. How many of you feel very comfortable that they know how to use whatever tools they have from OHDSI and create a concept set or a code list for a given condition? Raise of hand. 1, 2, 3. That's less than, okay, other than the teachers in here. Okay. Okay, 2 people. So by the end of my 30 minutes, everybody going to be a master in producing a concept set of a given condition. If I don't do this in 30 minutes, I fail and you fail. Okay, let's no pressure. Let's start this. So you already saw this kind of representation from Anna. But let's take this and apply this for an example. The example of the day going to be systemic lupus erythematosus. And I'm going to use the abbreviation SLE, because I live in the States and everybody uses abbreviations. So they're going to use lupus, but I'm not going to use lupus. I'm going to actually use SLE, and that's intentional. Okay? So let's apply that structure on something like SLE. So if you are familiar with US data sources and you are tasked with creating a code list, you'll be like, what are my ICD-10s or ICD-9s for SLE? That's what you want to try to get. So if you have no OHDSI, have no idea what these people do, you would go and you search SLE, and you'll find some codes in the ICD-10 world, something like M32, systemic lupus erythematosus. There it is, found it. That's the code I'm looking for. How else would doctors code this? It's obviously a perfect match, right? If you're looking in the ICD-10 world, you'll find the 710.0, also perfect match. If you live in the UK and you're using data from with read codes, you'll find something very similar, systemic lupus erythematosus, not otherwise specified. All looks perfect. If you have no idea what you're looking for, that would be a perfect match and nobody can argue with you, correct? Well, in OHDSI, we all know that people speak different languages. We are a network of international data, as Anna said. People speak different terminology, and we want to produce standardized evidence that we can all rely on. So we need to standardize, and for that, we have those maps. So we map, this vocabulary awesome team work very hard to map things into a standard vocabulary. And for condition, the community has adopted SNOMED as what it's called standard. So everything in the back from wherever the data source is coming from maps to a standard. And in this case, the SNOMED standard is systemic lupus erythematosus. Looks perfect, no problems. Now, everybody understand what's the difference between source and standard? Yeah, we all got this clear. Okay, perfect. Because you're going to hear this over and over in the next 3 hours. This looks great. Now, the reality is doctors actually don't use one code to represent one condition because health conditions can represent themselves in many different ways. And the data can be granular, can be not granular, it depends, it's a mess. So there's multiple codes that a physician might choose to represent a health condition of a patient, right? Because we all people represent our health conditions in a different way. So in the situation of SLE, a patient might show up actually with SLE where the physician knows that there's lung involvement. And look, there's a better code for this patient because it says lung involvement in systemic lupus erythematosus in the ICD-10 word. That is M32.13. Oh, we have to pick that code too. Are there more? And we need to pick the standard. Oh, perfect. There's a mapping for the standard. So we can pick the standard in this case, and it's perfect world. Now, Anna mentioned that SNOMED is actually hierarchical. That means it keeps knowledge, which is something beautiful about SNOMED that doesn't exist in the ICD-10 and 9, and that's why maybe it was adopted by the community as the standard. So SNOMED actually have this relationship where it says there's this idea of SLE, but it subsumes granular, more specific situation of SLE, and we're going to call all these things that SLE can present itself as the children. But if I take SLE, but I'm going to maintain that relationship where I'm going to say SLE has children, and in that case, it has this child of lung disease with SLE, also acute systemic lupus erythematosus. So both of these are subsumed with the parent of SLE. Now, in a perfect world, you're like, oh, I got it. Thank you, SNOMED. Thank you, OHDSI. I'm going to pick SNOMED. Its descendant got SLE. There's no way I missed anything. I'm not going to look at those websites of ICD-10 and 9, and because SNOMED it is. Your colleague will come to you and he said, no, you missed something. There's something called endocarditis due to systemic lupus erythematosus. That's a complication of the disease, suggesting that the patient has the disease as well. In this case, it doesn't actually live in the SNOMED world under systemic lupus erythematosus. In this case, SNOMED people decided there's another branch of SNOMED that is dedicated for the complication of a disease, and they put it somewhere else in the hierarchy. Now, if you don't know about it, you won't be able to capture it. If you don't understand SNOMED and sleep with it every night, you won't know. Obviously, no one can memorize a structure or a hierarchy of one vocabulary, so mind many different data sources with many different vocabularies with many different structure. So if our life was, yes, we have a standard vocabulary for condition, and I can just use it to find my conditions, and I just have to like keep doing syntax search, that task of finding your code list might take really long time and you'll still find errors. So in OHDSI, we are all big about standardization and reproducibility. So we can't really rely on how good a person is in finding syntax search across vocabulary. That's why we build processes. And around these processes, we build tools to make sure, one, our work is efficient and nice, but also, more important, reliable and reproducible. So if you or me or anybody does the same task, we end up with the same output. So every process has an input and an output, and Anna already showed you in this nice figure with how we come up with phenotypes, that starting with selecting the codes, is by relying on two inputs. That is the clinical definition. Before you ever come to create a concept set or a code list for a disease or any health status, you, whether you are a physician or you are never seen a patient and you are living behind your laptop, you have to understand what is it you want to try to find that concept set. And you need to understand that clinical definition. You can find it in ChatGPT, you can find it by talking to a doctor, but understand what SLE is before you go and create that concept set, because you will need that knowledge at some point. The other input, as Anna said, are literature review. You also might be like, I don't want to reproduce this. I can just find a paper that find the codes and say that those codes are validated. And I just want to replicate that. You can also do that. Nothing wrong with that. No matter what things are, our process is built by the person who's building the code, understand the clinical thing that they're trying to capture, and they have looked into what the literature suggested or what others have done before. Then you go through 3 steps. You're going to find your standard, and that can be one thing or it can be multiple things. We'll see. It could be one code and its descendant. It could be multiple codes and its descendants. It could be one code, descendants, and few other children. We'll see. Then you're going to check the source, because everybody care about those ICD-10 or 9 if you live in the US, because when you send your protocol to your clinical partner, they'll say, okay, what's the codes? I want to see that. So you want to check your source code all the time. The vocabulary group here are phenomenal, but they can make assumptions as they do those mappings. So you want to check those assumptions, and you want to make sure that this is what you're interested, because at the end of the day, that native data came with those source codes. And you want to assert that nothing went wrong during that mapping. And then finally, we have the last step is that after you have your descendant, you have your standard, looked at your source code, you're going to check one more time if there's something you missed. And for that, we have a recommender system called Phoebe that I'm going to show you. It's something that will work behind the scene to check what other codes you might have missed based on lexical, based on lexicals or based on relationships and so forth. And that will make more sense in the example. Okay. Any questions so far? Good? Everybody ready for SLE? Who doesn't know what SLE is? Okay, perfect. Now I can pretend to be an expert. So SLE is a chronic. We're going to read this. So that's a clinical description coming right out of OHDSI phenotype library. Who knows that OHDSI actually maintain a phenotype library that actually have definitions for common conditions, including the concept sets or the codes for these conditions? Perfect. So that's a place you can go to as well to find your codes. But in the library is built based on this process. So when we have a condition, we don't only use the label for it, but we actually provide the clinical description to make sure that this is what we mean by whatever clinical label. So in this case, from the library, SLE is described as a chronic autoimmune disorder characterized by systemic inflammation affecting multiple organ systems. Unlike localized autoimmune disease, which affect specific organs or tissue, obviously from the image here, SLE is a systemic disease, meaning it involves multiple organs and tissues throughout the body, potentially causing widespread damage. The clinical manifestation of SLE are diverse, ranging from mild symptoms like fatigue and joint pain to severe organ damage, including nephritis, neurological disorders, and hematological abnormalities. So it's an autoimmune disease, can hit anywhere in the body, and have multiple manifestation, and that's a representation of the disease. So now we have like this mental image of what is it we're looking at. Not very pretty, but diseases are not pretty. The second input is that literature review. I'm not going to tell you how we get this in OHDSI, but you can search Google, you can search Scholar, find me papers that worked on SLE and actually published codes for SLE. We do this also systematically, and we usually, as our teams work across the community, we usually accumulate that literature review, and we can summarize it in something like this. So here's article number 4 that used for SLE this ICD code M32. Article number 5 did something similar. Article 6 did something similar. Here's Article 6 also included L93. So you'll see multiple studies shows multiple codes. So you will never find something that have the same exact code list from all the papers. Depending on which paper you get to find, you'll have different codes. And that's another reason why follow the process versus find a paper and say, that's what I'm going to do and replicate it. Even when they say validated or an expert opinion looked at the codes or anything like that. So we're going to be better, and we're going to actually use that knowledge that people represented through Scholar articles as something that we know of, but not necessarily replicate 100%. But it's good something to understand of what others have done in terms of finding codes for SLE, for example. Here's a specific example of a paper where they decided that SLE is represented in M32.1 and M32.9. That's in the ICD-10. That's just a snapshot from the paper. Okay, so this is how we do it in OHDSI. Everybody knows Atlas? Anybody who've never seen Atlas in their life? Yay, okay. So we're gonna go to Atlas. I'm glad that, oops, I forgot to do one thing. I cannot type in front of people, so I'm gonna copy SLE right now from here. Look, Anna, I forgot. Here we go. I'm gonna copy it from your nice structure. Okay, so we go to Atlas. Everybody knows what Atlas looks like. You go to the search button, and you literally, all what you do is you copy the label that was given to you. In this case, SLE was the library that the term was given to us. Now, you do not hit search. you hit this nice, beautiful cart. You're gonna shop for codes. When you have amazing tools like the ones we have in Odyssey, we actually shop for codes and we're not searching codes. When you hit that cart in Atlas, what it does is that it relies on a recommender system in the back. That recommender system uses laxative matching, so the label you gave it, and it tried to find the closest standard code that matched to that, but it takes into consideration the record count that comes on those codes across the network of Odyssey partners. So it's gonna find for you the closest code, the closest concept from SNOMED that has the highest record count across the network, suggesting that that is the right concept that represents this SLE idea. So it's going to automatically go to the Conceptsets tab. I didn't touch anything. It went on its own. And then it's basically recommending for you your starting point. So in this case, it's recommending starting with systemic lupus erythematosus with all its descendants. I make it bigger. Hold on. Is that better? One more. Is that because I exited the view mode? One less? Everybody's okay? Looks good? Okay. So look at this magic. You didn't have to look at list of big codes and find where you start. It's actually recommending a starting point. Are we done? No, that's a starting point. That's just the first code. Phoebe is telling you, start from here. That's your best place to start with. Okay, so it started with that standard systemic lupus erythematosus with its descendant. You're going to save it in your atlas, and I'm going to save DIME and just use X and I'm going to save it. Okay, then what did we say in the second step? Okay, fine, I have the standard and all its descendants. First, I want to make sure, what are those descendants? Maybe under SLE, there is malignancies or something like that. You need to make sure what exactly your descendants. In this case, there are 30 concepts in SNOMED that map to that standard parent. You want to explore those concepts. Now, here is an atlas. You have a beautiful ability. If you have long list of codes, you probably want to focus on the one that actually show up in the data. So you have something called RC and DRC. Anybody knows what RC stands for? Not instructors. Okay. Yeah. No. Record count. So this tells you how many records in this particular instance the atlas is built on is loaded on this particular one code. You can sort, and DRC is the records of this code and all its descendants. So it's catching up in the hierarchy and telling you how many codes map to this entire full of hierarchy. So, and then you can sort. So here we can see we have 30. That first one is just SLE glomerulonephritis syndrome. Here's the first thing you're going to notice. A lot of these ideas should be already presented in your clinical description. It tells you SLE can present in different organs, and here you're going to see all these different types, which should make you feel good because, yeah, that's exactly what I was expecting. Because when I read what SLE is, it talked about involvement of lung, it talked about skin, it talked about all these things. So you can explore all those 30, focus on the one with high record count, and it looks good, you move on. The next thing we said we have to check what? Source code, because those mapping people might have done something wrong, right? So we're going to check that. Now, depending on what you care about, you can focus on one vocabulary versus the other. The atlas is going to show you the representation of all the source code because, again, the vocabulary team works with different source codes across the network. So they don't only maintain the relationship between ICD-10 and SNOMED, but rather ICD-10, ICD-9, MEDRA, READ, and all of this, anything that is part of the Odyssey community. So since we are in New Brunswick, we're going to focus on US-centric stuff. So for example, you can look at ICD-10 CM, And here you can also sort by the code to understand the hierarchy, to understand the codes if you are familiar with ICD-10. And you will notice that it's capturing M32, M32.0, basically all the M32 branch. And they all say systemic lupus erythematosus. They all look good. If you're not sure, you can call your friend doctor who maybe knows a little bit more from you, but you can look at this and explore it and make sure at least semantically it looks right. You make sure there's no malignancy here or, I don't know, type 2 diabetes or anything weird. Okay, are we done? We have one last third step. We found our standard. We found what it maps to. The source code looks good. But does everything represented in SNOMED belong to that one? Does everything in SLE necessarily belong to that SLE and its descendant? No, remember in the first slide, sometimes the same idea represents somewhere else. So how would I know that if I don't already know the full structure of SNOMED? That's when the recommender system gonna help you again. Because you click on recommend. In Atlas, it's gonna recommend for you some codes. Again, running that tool called Phoebe. It's gonna tell you basically in this tab here, why is it recommending it? What's the relationship between those things presented on the screen and that SLE and descendant concept set that you already have in your shopping cart? It does things based on lexical match, and it also look at the relationship in terms of ontology. Now, here's the special thing about this. It's not only taking the term SLE and based on that looking for lexical matching, it's actually taking SLE and all its descendants, every term in that descendant list, and look and see if there's some relationship with other terms that you are not have yet in your code list. So it's more than just a search, because it's taking the entire hierarchy and look and see if there's some relationship that are hidden there. Okay, the first one I'm gonna look at is ontology parent. What that tells you is that the recommender system is telling you, you're starting from SLE and all its descendant, but sometime you might want to hop up in the hierarchy, take a parent, because maybe the less granular idea is relevant to you, and maybe that's what you want. For example, you can look at the list, but here, disorders of lung, that's too broad. That's definitely not what I'm looking for. Central nervous system complication, way too broad. You go all the way and you're like, okay, this is bad recommendation. I don't want this. But then you find this, lupus erythematosus. And you should pause here and think, wait, I want SLE, but what is this? There's a code for only lupus erythematosus itself. Is lupus the same as SLE? And here you're gonna pause. Now, you can call a doctor and ask that question, but before you can actually look at some empirical data to help you. So we're gonna click on that. And now Atlas is gonna open for you that concept. The first thing you're gonna see is you want to understand the hierarchy in SNOMED for lupus. You want to understand what's the relationship between SLE and lupus and all of that, the full hierarchy. So you will see that lupus itself, that's it, lupus erythematosus, is a child for disorder of connective tissues and autoimmune disease. Makes sense because you know it's an autoimmune disease. And it has children. You can sort them like this. And you'll see that the first child is SLE. That's the kid you're interested in. And there are other children, like drug-induced lupus erythematosus. Okay, maybe you're not interested in this. Neonatal, maybe you're not interested in this. But you obviously see that there's a group of people who has lupus and all its descendant, and most of them, that's 54 million record, most of this, the big majority, are actually SLE, the thing I'm interested in. There are 2.7 million record here that are loaded on the general idea of lupus erythematosus, which could be SLE. So because SLE is a type of lupus, right? Because it's the systemic lupus erythematosus, not necessarily, while lupus erythematosus is a general idea of any lupus. And then you might ask yourself, what do I do with those 2.7 million record? There's a lot. They're going to affect my record count. are these people legitimately could be having SLE, or they just undefined? Why did the physician decide to give them that lupus erythematosus code versus SLE code? Remember, everything is coming from some source data and maybe not necessarily coded by SNOMED, so you might want to check and see where are those 2.7 records are coming from in terms of source codes. So you can go into related concepts, that's navigating that relationships. And you will go to the relationship tab. Here are all the different relationships that OHDSI maintain, answering the question of, is it only the parent and the children, or is it only the source? No, you have plenty of relationships that are kept and exposed for users. But in this case, you want to look at what does that standard map to non-standard. And you want to find those ICD-10 codes or ICD-9 codes if you're interested. Oh, it went away? Oh, I clicked the wrong one. It's standard to non-standard. Here we go. Okay, so you'll see that that lupus code actually is coming from those two ICD-10 codes. So other local lupus erythematosus, well, remember our clinical description? We want that systemic one. So we definitely, just relying on that clinical description, don't want this code. Now, here is another ICD-10 code that says lupus erythematosus, and here's the ICD-9 code that says lupus erythematosus. Here's a judgment call. Do you want these two or you don't want these two? One indication might be for you the ICD-10 vocabulary itself. It's taking them under this family of L codes, while it's putting SLE in the family of M codes. And you might say, well, that's clearly not the same. I want to stick to those SLE, and I want to be more specific. If you want to rely on your clinical description, you would not include those codes because your clinical description said systemic lupus erythematosus, and its main feature is that systemic involvement. You can always, at this point, call the clinician and see if they are interested in these codes or not. But the point is now you know exactly how much it matters because you had 54 million records for SLE, and you know that there's about 1 million, maybe 2.7 million that if you to add those codes, those will affect your record count. But you at least have some idea of how much this matters before checking with the clinician if those are codes that are belong to the idea of SLE or not. Okay, finally, you're going to go back to your concept set. You say, okay, I don't want those based on my clinical description. I'm going to go back to the command. Remember, we based the relationship based on ontology. Now I'm going to see if I'm missing anything in lexical. Is there any other terms, any other concepts that are close to the concepts that is SLE and its descendant that I'm missing? So you look here and you're like, okay, I don't see anything interesting, but look at this. Disorder of immune function due to systemic lupus erythematosus. That's the idea of the complication. And here the recommender system picked it. Now you're like, oh, I wonder if there's more like this. You know what? This is a long list of 35 codes. I don't want to look at them one by one. I just want to see if any codes actually include SLE in the name. So you can filter on that, and you will find here 17 codes, all of which actually have rash of systemic lupus erythematosus, joint disorder due to... So all these complications of the disease are sitting here, and we would never have found them unless either we memorize SNOMED or we use the recommender system. And you can simply say, oh, all those are legit. I'm going to take them with their descendant, and I'm going to add them to my concept set. And then you go back to your concept set, and now you have 18 concepts of codes that represent systemic SLE. You always want to optimize because you want to have a nice code list that is not long, that take into account that relationship. If you have a parent and its descendant, you don't want the child to show up again in your list because it's already subsumed, right? So you can optimize. That's something that Atlas allows you to do. And then you want to overwrite the concept, and now you have a concept set of 13 different concepts that are concise, that represent SLE, and in this case, not only SLE, but SLE and 3 days complication. Okay.
You mentioned this optimization step in this quarter is what did you click to optimize?
It's right here in Atlas. So whenever you are in the concept set tab, you always have that optimize. So you have a list of codes. Say you have SLE and its descendant, and then you have SLE with lung involvement. And SLE lung involvement is a child to SLE, and you already have the descendant. So it's redundant that you have them both. So what it does, it's remove that redundancy. It creates the most concise concept set for you to look at without repetition. So it removes the redundancy.
As I go through this process, I'm kind of like throwing
Yeah,
things there and I
exactly. And sometimes people worry, well, I don't know if I want this code. It may be there. Doesn't matter. Add it because you can then optimize. No, it's verbatim. So it's producing, it's not taking into consideration the descendants relationship. It's recommending the code, each code on its own. So it could have something and its children. And that's why, again, that's why you have that optimize. You can include, you don't have to think, is that already included or not? You can click it and then optimize. And if it was redundant, it will disappear.
Once you've gone back and added concepts, do you go back and repeat the process of checking the source code?
I knew you were gonna. Yes, I personally do, because. Yeah. Oh, sorry. So Andy asked, okay, now you added bunch of standard based on like the wording SLE, but do you go back and you check what does that mean in terms of source codes? What are the source code that you brought in when you added those recommended standard? The answer is yes. Every time you add a code, if you add it based on standard, you want to go back and check your source codes. And here's, for example, here is my ICD 10 cm now became 12. And then you will see that it basically added more of the M32 that were not in there yet. Sometimes it actually has no effect in your source code because in reality, SNOMED is way more granular than others and have more ideas. So you will see a code and it will look really good, and then you'll add it, but then it doesn't add any source. But if your data isn't SNOMED, then you're capturing those records. It won't hurt you. You can tell because the recommender systems show you the record count. So you could tell, is that a code that is never used and doesn't exist in the source world, or does it? Because if it has counts, then there's some records coming from somewhere. Any other questions? So the question is, the atlas I'm showing, which is J&J Atlas, doesn't have, I think, Phoebe. The atlas she has doesn't have Phoebe, doesn't have the recommend. So Anna can talk. The demo atlas that we're going to use today that is in the public domain looks identical to this one.
Yeah, so this is the J&J Atlas, which we use just for the speed purposes, so that it's fast and you don't have to wait until something loads. The public atlas that we're now going to use for exercise is Atlas Demo, and that Atlas Demo has Phoebe in it. What it actually is just the UI. What sits in the background, is the table with the recommendations that we produced at a certain point. And if you have your Atlas instance, you can download this table, upload it into your Atlas, and it will have these very same recommendations. And Public Atlas has it.
I feel like I missed something fundamental in the beginning, so please excuse me if I need to go back. All this search is you mentioned going through the literature and kind of skimmed over about like let's not talk
Yeah.
about how this name is going to OHDSI. So we're searching here all
Yeah, and you're talking about. I'll repeat the question, just clarification. You're asking about this search.
So basically, we're searching something and we're looking, what are we searching?
Yes. So the question is, we talked about searching and that carts and all these things. Where are all of this coming from? What are those vocabulary? So you are searching the entire structure of OHDSI vocabularies. Where does it come from? It comes every time a partner ETL their data into the OMOP CDM from their source vocabulary, from their source data. They go through the process of mapping their source code into the standard, because the CDM itself is represented through standard terminology. And so they contribute that knowledge they have based on whatever their source code into the community, and then the vocabulary team in the community maintain those relationships.
So, is there some curation process, like, or because you mentioned sometimes we don't know why the physician put this code, and I missed this a little bit. So, how does like some of the relationships? Sometimes you see that okay, this is a more general concept, and you're saying we're not sure why this was included. But how does this process work? About the relationships that eventually make it to this set of.
Yeah, I think the whole vocabulary maintenance.
So there are actually two different. I think you're touching. Yeah. So the question. Well, no, it's kind of hard to repeat it. So we mentioned at a certain time that we are not sure why clinicians may code something as a lupus, and the question was how these relationships go into vocabularies. So I think we're mixing slightly two different things. One thing is how clinicians code their patients in practice. And they can have different coding practices. And the very same, for example, we talked about lung involvement in lupus. A clinician can code this as lung involvement in lupus, or they code it as lung disease and lupus. So there are, and we know for sure that different physicians, even within the same hospital, use different coding practices. So that is one thing. And this is why we want to follow the process, because if somebody gives you a list of codes and they tell you that this is what I used to code my patients, it doesn't necessarily mean that the clinician next door will use this same list of codes. So at this point, what we want to do is we want to be comprehensive. We want to capture as many codes that represent this clinical idea as possible. Correctly, of course. So this is why in our phenotyping process, there are subsequent steps that allow us to assess whether we made the correct choices. But at this stage, we want to be as comprehensive as possible.
It's also like this comes from the data, and obviously this is observational data. So that decision about which code to use have been done somewhere in some clinic, in some hospital, and we're just retrieving the data and trying to make inferences based on that.
Okay, so if I understand correctly, basically you maintain all these relationships that have been submitted through the community, and that's why when we're looking at the search results, we need to make a call whether it makes sense.
Exactly.
Right? Because there can be some things that are quite idiosyncratic.
So that was the second part of the question. So clinicians themselves may use different codes. So you may see different codes here as well, about which you will need to make a judgment call about whether you want to include them or not. Then there is a separate part, which is OHDSI vocabularies. What vocabularies are is we import all of the vocabularies, ICD-10, ICD-9, SNOMED, and we build the relationships between them. Relationships on average are exact match. On average. Are exact match, which means that you will get the same idea in ICD-10 mapped to the very same idea in SNOMED. So there is no impact coming from the vocabulary mapping. And there are a couple of papers written by George Krapsak on that topic that actually shows that for most of the things, the mappings have no impact on your patient counts. Then there are other cases where the mappings are associated with the loss of information, but that is a kind of different area, which I don't think you were exactly asking about, but correct me.
Yeah, no, I think we got. Yeah. Now, every vocabulary on its own comes with its own dictionary. So, like, there's ICD-10. This tells what this code should be used for. If that's also another information that you would be looking for.
There was another question somewhere. Oh, no. Yeah. You go ahead. You beautiful lady.
So can, just a question. I know there's the hierarchy that you can see in Athena. Can you get to that hierarchy here? This sort of the first question. And then the second question is just to confirm the question on the recommender. It's basing it off of the existing hierarchies, not like relationships with your data set.
Answer this question. These are vocabulary questions. Yeah. So two questions. The first is hierarchy in Athena, which is another website to browse ontologies in the OHDSI vocabularies, and Atlas hierarchy the same. They are the same, with the exception that it depends on which atlas you use and which vocabularies you loaded in. We, for example, have Athena right now has the most up-to-date vocabularies from August. This, for example, version of Atlas has February release loaded. So there will be difference simply because of they have different versions of vocabularies, but in theory, they can be absolutely the same. Now, the second question was about recommender, and maybe we'll spend more time on that then. So there are several categories. One is lexical match. Lexical match is just looking for another strings that look similar. That's it. Nothing else. Then we have another relationships, ontology parent and ontology descendant, not shown here. These recommendations are coming from vocabularies. So we go up and down the hierarchy and we show you the parents for you to think about them and descendants for you to think about them. There are two more recommendations that, so it's just quote unquote. It's just a pair of quotes, nothing else. Then there are other two types of relationships. Patient context, where we use patient data to look for codes that co-occur. So there you would again see a pair of the things that co-occur together in the patient data. And there is another relationship that we just introduced a couple of months ago, ontology related. That recommendation uses lateral relationships in vocabularies to get your recommendations. But it doesn't really do anything beyond. So the only place where hierarchies are used is for ontology parent and ontology descendant.
But it's looking per code, not taking into consideration the relationships. When it recommends, when it looks at those, like when it picks something. In the first step, it actually takes into consideration the descendants relationship. But then when it recommends, it's recommending verbatim codes.
No.
That's because like.
So we used, to generate this set specifically for patient context, we used 6 or 7 data sources that were at our disposal at the time. So it will give us co-occurrence for the things that were in those databases. So for example, if you have primary care data from Australia, then probably these recommendations will not be terribly useful for you. And the way to improve the recommendations is actually contribute your data, because that was a network study where we asked 22 data partners to submit their aggregated data to help this work. So if you want to see your codes or know that these recommendations are directly applicable to your data source, you can talk to us so that we incorporate it.
So that end output of the recommender, you
I'm sorry.
a bunch of conditions that were secondary to or due to.
Oh yeah, I think actually.
So how has OHDSI been handling these situations? Because I'm sure that there are several variants of those same conditions that are due to secondary causes of some form or the other. And in the relationship tables, like what relationship is OHDSI placing between these? And like how
No, that's good.
given that this is such a common thing, common occurrence that
Yeah.
So we do not curate these types of relationships, but SNOMED sometimes, because we really do hierarchies and mappings, because that's what people care about. But here specifically, sometimes SNOMED, we will have relationships from SNOMED, and for example, this condition will have cause linked to the cause, and the cause will be lupus, and in SNOMED, these relationships do exist, but they're not too comprehensive. So you will see them for some of the terms, and then you will not see them for other terms. If you know how to use this relationship, it's totally there, and you can totally use it. And for example, Vlad will talk about measurements later on. In measurements, codes have links to, for example, specimen. So if you want to retrieve all of the labs done on blood, you can do that using relationships that LOINC provides us. But we ourselves do not curate them. We just get what they give us.
Searching by recommended function, you said that the recommended codes are pulled from the most prevalent codes within OHDSI. Are those updated live or are they updated like
You killed Anna by this question. It's on her to-do list to update.
So we update, the original study was done 4 years ago. 4 years ago, and we got 22 data sources. We had a nice representation of Asian data sources and US data sources. We didn't get a lot of European data sources, for example. Since then, we haven't updated the data, which means that the counts are from 4 years ago, and we don't have new counts. And one of the things we wanted to do is A, engage more data partners and actually update it, and B, ask them to participate in the network evidence network led by Claire Blacketer, where the goal is exactly to collect more information about the data sources, and then we can reuse this information to update this. So we've been trying to push that initiative so that we can also keep this up to date.
would that update automatically for people using Atlas or?
Yeah.
Who's ready for exercise? Oh, one more question. Go ahead.
Where you had the little shopping cart,
Yeah,
where was that?
that's search. So your starting point is always that search button here in Atlas, and
Under the OHDSI Atlas, I only have the search.
wait, it's there
In the public atlas we have it.
in the demo.
In your atlas you may not have it, but in the public atlas we have it.
Yeah, we can maybe work with her. Okay, so one more question. Where?
Say it again? What exactly? What exactly? So what exactly is based on the hierarchy? So what we have in Atlas is a UI to do different things. What sits in the background is one of the things is vocabulary tables. So vocabulary tables have all of the structure that we talked about previously. Concept for all of the content, concept relationship for all the relationships, and concept ancestor for the hierarchy. So these tables are stable, and you can download them from Athena, and they are used across different OHDSI tools, but they are just stable.
And then Atlas
Does that
expose that.
Yeah. Does that answer? I'm not sure I got your question though. We'll come to you.
We'll come to you. Okay. We took more time, but we'll see how much we digested right now. So we're gonna do the same exercise that we did for lupus, but we're gonna do it for rheumatoid arthritis. So here I'm showing you a clinical description of. Whoops.
I would just say it might be the same thing. There's Atlas-demo and then there's Atlas.OHDSI.
Yeah, we'll do Atlas-demo is one that.
So everybody gonna go to their Atlas. They're gonna use their computer, go to Atlas, You all want the next slide. Here we go. It's atlas/demo.odyssey.org. And the task is to create a concept set for, for RA, or rheumatoid arthritis. Here is what rheumatoid arthritis is. I'll make this maybe bigger. And here are the codes that other papers have used, just for your reference.
So don't touch the apples yet, just open it, and we're going to direct you on how to do the exercise.
Yeah, just open atlas/demo.odyssey.org. That's it for now. The task is to create a concept set inside Atlas that represents RA. Remember, the step is like that. We understand the clinical description. We look at what others have done. And then we start with finding the standard, starting from that search button. But, okay. I'm going to keep the screen on this one, so we know what RA is. It's too small. Too small, too small. Let's see. Okay, maybe I can just like go over it. Okay, it's a chronic systemic inflammatory disorder. Oh, I can't read it, it's too small. Primarily affecting the your joints, your knees. Okay, yeah. It's characterized by I can't read it. It's really slow. Here we go. Here we go. Ooh, I fixed it. Touch screen. Okay. That's all what we need. Okay. So everybody have the clinical description? Did everybody get to Atlas? Everybody got to Atlas? Full count? Okay. The T is? Most important. Okay. It's open source, so that means a lot of people use it because it's open. That means it can crash in high use times, like today. So we're going to work in groups, work around your table. Let's have one person in the table clicking the buttons in Atlas, and your task as a group to create one concept set in Atlas. So let's keep it light. One person, click the buttons in Atlas, go to the search button, type rheumatoid arthritis, and take it from there. Okay. How do we feel? How did the exercise go? We could replicate the steps. Andy doesn't like it. Okay. Show of hand if you were able to replicate the steps. 1, 2, okay. There's one in every table. That's promising. Okay. If you followed the step and you looked at those codes, you could have, and hopefully you ended up with 14 concept set for RA that looks like that. This is the answer. This is the definition of RA in our phenotype library. I got there over and over when we were demo for this through the steps, but you could miss something. If you still have a question about it, feel free to contact any of us. Anybody reached to 14 concepts? No. Okay, I saw somebody who reached to 11. Somebody reached 11, yeah, so that was close. We just needed to click a few more buttons that were probably for. But essentially, it's rheumatoid arthritis, all its descendants.
We should comment that probably it happened because people didn't go to observation and we actually didn't even recommend them. So we said something like, okay, just click condition.
Yeah, which I think reached to the 11. If you reach to 11, you're very close. That meant you just didn't look at some observations where the rheumatoid arthritis exists.
What we got stuck was when you bring rheumatoid arthritis, you get way shouldn't have gotten confused. You should have just done the comprehensive rheumatoid arthritis and then supplemented.
Yes, but there is some clinical judgment at some point of like, do you want to go up higher and take everything?
So this is down.
This is down, yeah.
Right, so juvenile rheumatoid
Yes.
arthritis is included, but the IC codes for juvenile rheumatoid arthritis were not included in those studies.
Yeah, so that's what other study does. Yeah, obviously, yes, yes. But if you notice, I was going to say that 99% of the time, those things that you will see that maps us through SNOMED, but you don't see in those studies, are things have a relatively small contribution to your full record count. And then you'll be like, I don't need to, you either make the choice of, I'm not going to include them because I want to do what others have done, or I would include them because I want to be comprehensive, or I don't want to include them because I know that I'm not interested actually in juvenile because my research question does not include that subset of patients. So there's reasons why you might make a decision. The point is the tool exposes all these choices for you, so you are comprehensive to Anna's point in terms of you saw everything possible code that you might include, and you want to make judgments, include it or not include it, based on the research question, based on the clinical judgment, based on the record count. It doesn't matter. Why do I kill myself with it?
Pragmatic question, because I know that there will be probably a lot of people asking you the same things. How extensive is Atlas documentation, and is there a place where the columns are explained, the relationships between columns, what means what?
We have demos. We'll
Yeah.
point you to do that.
Yeah, there are multiple.
Can we go there first before
Yeah. Technical questions about Atlas. There's so many demos for Atlas that we will link people to. Okay, time. So we're going to move on.
So how many concept sets each?
So we're going to remove the observation. So we're going to say how anybody reached to 11. I know somebody there and somebody there. Okay. Chocolate time.
We have more chocolates than subsequent.
We can also share the slides, so those steps, one by one, are shown for both the examples. Like something that will look more like that. It doesn't show here, but yeah. Here. Like it would go through the exact click, click, click. So you could follow the steps. Okay. Now, obviously, somebody while we were working came and asked a genius question, which is, okay, like this is just a code list representing RA, but if I'm interested in people with RA, maybe there are other domains in the data that I want to look for. Maybe it's not just people with a code of RA. Maybe I want to look at measurements. Maybe I'm going to look at other things. That's exactly why we're going to go to the next presentation that actually talk, yes, clinic conditions or phenomenon of health don't just exist in one domain. They exist in multiple domains. And so each of domain has its own way of how it codes itself. So now we're going to go to measurements.
And we're going to have a break right after that, so we follow through.
Give me a second to open the presentation. Yeah, color changed. Hello, my name is Vlad, and I'm going to lead this section related to the measurement concept set assemble, and we'll explain how we can work with the vocabularies to define some measurements. Yeah, you already finished the exercise on rheumatoid arthritis and how to create the concept set for conditions, but sometimes you really need to enhance your phenotype or even find more patients. And one of the example we picked for this particular tutorial is the measurement of C-reactive protein that is maybe useful to determine the disease severity for rheumatoid arthritis. This is a substance produced in response to any sort of inflammation, and it's typically measured in peripheral blood of patients with chronic inflammatory conditions. So that will be the focus of our demo. When we are thinking about the measurements,
we should imagine them as multi-component constructs with a key element as a laboratory test, as a sort of combination of analyte, specimen, and procedure used to determine the result. All these lab tests are tightly linked to some values, either represented as text narratives or represented as numeric results. And for numeric results, it is some sort of obligatory part to have the units of measure that pre-specify these numbers. When we map our example with CRP to this particular schema, we will find such a result. CRP in blood, plasma, or serum will be mapped to the lab test. Narrative, normal, or any kind of elevations or below reference range values will be stored in categorical fields in CDM. Numerical values obviously stored in number field, and units are also associated with proper unit fields. What is also important is to understand what is your data was, what type of data you transform to OMOP. And honestly, I want to name the slide, just manage your expectations about your data. So this graph represents how diverse the data sources converted to OMOP are in terms of completeness of laboratory records and diversity of laboratory facts that are hidden within them. This is maybe some sort of arbitrary, but let me explain. For example, in claims data, you will find lots of different distinct laboratory facts, but they are only facts that measurements was performed or not performed. But at the same time, EHRs typically contain lots of other relevant informations like numerics, categorical results, and diverse number of measurements facts. The semantics of or meanings of the measurements within these sources are represented differently. And technically, there are two major buckets of such data. One of the inputs are free text in nature, and the painful story about this free text nature inputs is that they are really super common in EHR data sets, and we have to convert them during the ETL process. And they may vary. They may be like just simple acronyms or subtractions or full-fledged names. The other inputs are structured. They are controlled terminologies, and the measurements within them may live in different vocabularies. In some unexpected, like ICD-10-CM, where we want to find and typically found conditions, or more obvious, like CPT. And the other story that lots of EHR systems use Loing coding for measurements, and that's the reason why I've put it to this slide, because in some cases, codes that we assume in OMOP world as standards may live in your data already. All of these entries from the slide should be mapped to standard targets in OMOP world, to standard terminologies. And in world of measurements, there are basically two major players. One of them is a SNOMED. Let's look at this hierarchy. So it's quite simple, but maybe tricky. SNOMED is organized into the hierarchy in OMOP vocabularies. When the code with less detailed names are parents for code with more detailed names, and they are linked via subsumes relationships. And the other relevant story about the codes that lives within SNOMED, they have lots of lateral internal relationships that pre-specify this. Technically, they are used to create these names. For example, has components, C-reactive protein, so you can browse through these relationships and this attributive concept to detect the proper target. The other player in this game, as a standard vocabulary, is Loing. We can observe quite the same behavior within Loing. It is also organized into the hierarchies, with one small exception. In SNOMED, all of the codes that organize the hierarchy are standard ones, and we assume that we can use them as proper targets, because they are likely to be used in coding. In Loing, the parental entries are hierarchical, and they are designed to group nodes of related concept by semantics. So they will not be used as target in OMOP instances, in OMOP vocabularies, but they are really useful to manipulate with LOINC data subsequently. So SNOMED and LOINC have separate hierarchies. What is also important to understand is that in measurement domain, in majority of cases, SNOMED codes have more broad and undetermined names compared to LOINC. LOINC is super precise. It specifies the analyte, the specimen, and the type of measure. And that's the main reason why the vocabulary team create the hierarchical relationship between SNOMED as a parent and LOINC as a child. So at the end of the day, all of your codes that exist in source data will be mapped to this standard, either thanks for guys in your team who are running ETL, or thanks for someone from the vocabulary team who did this job for you. Yeah. So let's discuss the algorithm, how we're going to work with concept set assemble, because we already have the targets that are aligned in the hierarchy. So first of all, we have to define the codes for laboratory test itself. Then we have to pre-specify the thresholds and exclude implausible numeric results. And also, for sure, we have to define and link the correct units. So at this step, let me switch to Atlas. I'm still not sure how it works. Maybe you have some questions already? Oh, reload. Okay. Thanks. Wow. Yeah. It looks like it works. Let me create a new concept set. Ah, okay. It loaded. Let's create a new concept set, CRB, Global Symposium, and save it. It was saved, thanks. Okay, let's search for C-reactive protein in general, the general term we have in mind. And look at the output. Yeah, I'm using just a generic search box, not a cart. And let's look how the standard codes within measurement domain are represented. So I filter everything against standard codes, pre-specify the domain with measurements, and yeah, we'll sort this output based on the descending record counts. And I will find that the highest number of codes, the records, are associated with C-reactive protein measurements within SNOMED domain, or within SNOMED vocabulary, and that's the same idea I've tried to show you in the slides. That's technically SNOMED is the parent for the LOINC. So let me pick this code and include it into our concept set and start the evaluation. I also pick all the descendants and switch to concept set tab. Okay, so we have only 19 codes included here. And now we have to evaluate, do they fit to our initial quite simple definition? So we know that C-reactive protein is something that is measured in blood of patient and represented as level. Let's start the evaluation and inclusion or exclusion of some codes. For example, CPT4 codes. There are several CPT4 codes, likely originated from claims data, and we technically want to exclude both of them because they are related to some measurement panels. One of the panel is infectious disease panel, and we don't want to include the patients who has active infection. And the other one is pediatric. So these codes will be excluded in code-by-code basis, and I will add them to our concept set expression with the flag exclude, and in advance put the descendants. There are two other vocabularies that are left. One of them is SNOMET and the other is LOINC. Let's look at the SNOMET entries. They are the parental entry we have with most codes associated, with most records associated with it. And all others seems to be quite good. They do not pre-specify the sample, however, plasma and serum is specified for two others. So I would advise you to store them and switch to LOINC, because LOINC is much more complex in this case, how to handle it. There are 13 codes to be reviewed. In this particular example, they are already ordered by record count associated. And let's look at these codes one by one. So this one, C-reactive protein mass per volume in blood by high sensitive method, is super good for our definition. The same is true for the second one. Oh, sorry. I expect that it will be the blood for some reason. Yeah, but yeah, this one with quite huge number of codes is not that good, because this is a C-reactive protein mass per volume in body fluid, and definitely not a blood. So that's the reason why we want to eliminate these codes. You already know that the LOINC also organized into internal hierarchies, and I want to show you how to make this magic happen. So I switch to the hierarchy tab. This is a visual representation of the concept ancestor table that we will leave in your CDM instance. And go to the parents folder and find the C-reactive protein in unknown body fluid by chemistry non-challenge, this hierarchical concept. I will add it to our concept set expression and enable exclusion for all the descendants. So now our concept set lost two codes in LOINC. Let's keep doing our exercise. We will keep all the serum and plasma, and we will find the same situation, that the CRP was measured in cerebrospinal fluid, CSF. And we will do the same. We will go to the hierarchy and exclude these codes. Exclude descendants. So yeah.
Once you see, say, for example, C-reactive protein found in cerebrospinal fluid, you probably could exclude it right there.
Yeah, for sure, I can exclude them code by code from the included code list, but the reason is that I want to have my concept set expression quite precise and tight, and not create any redundancy, and be sure that all of the codes that may have quite the similar semantics, like shared the specimen, like cerebrospinal fluid, will not be included definitely. So this approach with hierarchy-based subtraction is better than exclusion of code by code.
Correct. Especially if the list is long. Like here, the list is short, and often with measurements, you have like hundreds of measurements. So you don't want to do it one by one because it's easy to miss some of it. But Vlad nicely showed you how to use hierarchy to exclude a bunch of codes.
So yeah, you can use the hierarchy as it was in case and for conditions to include the concepts, but at the same time, you can use the same structure, the same hierarchy to exclude others. So for this particular exercise, that's technically it. So I don't want to grab your time and show how to process other codes, because they looks like they are okay. And let me switch to the presentation and discuss very final steps in our work. Yeah, so we finished with identification of laboratory tests and the codes that are associated with them. And now we're going to find correct numericals and units. So to do this, you are typically run the literature search and identify the all possible variations of units of measure that are associated with the codes and measurements of substance you want to describe. And in this particular case, the most prevalent ones was milligram per deciliter or nanomole per liter. What is also helpful is to understand what is your data is. And there are lots of OHDSI tools that can help you to characterize your source data and the resulting CDM. For example, ARIS reports. And for the codes we extracted, the most predominant unit of measure was milligram per deciliter. That is why I'm going to focus your attention how to set up the thresholds associated with this unit in particular. So we know the most prevalent unit, and then we have to define the numeric results that are considered proper for our use case. So there are several ranges that exist for CRP measured in milligram per deciliter. One of them is a normal range, that below that 0.3 milligram per deciliter. And there are several ranges of elevation. One of them is septically high. That means that the likelihood of bacterial infection observed in this patient is very high. That is why we want to exclude this. So at the end of the exercise, our resultant definition will include the concept set for measurement, the numbers that belong to the range between 0.3 to 10, and are pre-specified with units, milligram per deciliter. And that's technically it. Thanks. Mm-hmm. Yeah.
Yeah, I have a question for labs. Like, for example, SCCP also an RA lab that have pre-preference So for labs, like SCCP, have pre-preference panels, so the range for models want to be different from every single one. How is that going to happen?
Question is normal ranges in CDM. Do you want to? Okay. You can go ahead if you want. That's fine.
Well, actually, lab knows more about that. You should check. So you will need to know. Yeah, you're doing this. You will need to know more about your data. So this is one of the things that people sometimes have worried. They kind of assume, oh, okay, it must be this range, and it must be this unit. But if you look at your data, you usually see a little bit different picture. Weird units, weird ranges. Is for each panel, if you know that each panel is different, you will create different concept sets for different panels, and you can specify the ranges there. But you first need to check this assumption while looking at the data.
So when you were doing the exclusion on the hierarchy of LOINC, so you're using the LOINC parts, I'm
Yeah.
presuming, in doing
Yeah.
that. And so when you showed that, basically you were just saying that this specific LOINC part is, I'm excluding that so that I get whatever it is I want to get. Is that correct? If I
Yeah.
was going to do
Yeah,
it
yeah.
in LOINC.
Yeah. So you will do it based by the LOINC parts that obviously should be excluded. Yeah.
Okay, thank you.
For the categorical values, those are, you're laughing already. Those are often hand entered, and so sometimes they have typos or creative spellings or variations on a theme. How do you handle getting those to standard concept?
So they typically should be mapped anyway.
So just tedious ETL work.
Because you do the CTLs.
So
How do you handle when you do ETLs?
we perform the mapping. So that will be the most using different techniques. So you should just map these values, and there is no other way how to work with them. Or you will just look at the source values with all these typos, etc. So
Thank you.
Oh, so Andy is suggesting coming to the health system work group?
Because they're building a category, you know, a library of those categorical mappings that people, health systems have done, so you don't have to start from scratch.
But that depends on what was done for your ETL. So if you're not doing ETL, it's just nice to like double check what they did. Are there any other questions? All right. So then we will take a break. We will take a 15-minute break. So please be back. Okay, let's make it 18 because we feel like we need a break. Let's come back at 3:10. And after the break, we will go through 5 scenarios with drugs. And that portion, we got a lot of good feedback. We've done it multiple times. So please come back. If I don't see you after the break, I will be very, very sad and disappointed. And we have more chocolates. Okay, we have pumpkins and if our TAs are not gonna eat all of the chocolate, we'll have even more. So let's take a break. Come back at 3:10, and we will go over drugs.
Okay, let's start the last part of the tutorial. So my name is Oleg, and now together with Polina, we will walk you through drug concept sets. We do have some positive feedback from the audience, and I hope that not the only reason for that is that drugs are the easiest part. So I hope there are some other reasons. And you've already seen this slide structure before. On the left side, in orange, you can see the source local terminologies for drugs, and on the right side, in blue, the standard terminologies for drugs. So nothing unusual here. We have structured source, like Eric's norm and NDC, and also some unstructured local terminologies. Everything is mapping to some standard. Standard is Eric's norm. So for us, it's kind of a win-win situation when you can spot the Eric's norm as a standard codes in your data. So nothing unusual again. But what I really want to highlight here is that there are other vocabularies like CPT4, HICPICS, or CD10 PCS. And you would expect procedures to be there, you would expect observations to be there, and maybe sometimes visits to be there. But in reality, there are also some drug codes in these vocabularies that are mapped to standard Eric's norm and Eric's norm extension. So just keep it in mind. And there is, in drug, there is only one classification, which is ATC. We'll talk about this later. So basically, what is a drug? A drug in OHDSI is a combination of attributes, and the only one attribute is essential. This attribute is an ingredient. In our case, it's nicotine. And other attributes like drug strength, dose form, they just add information on top of ingredient. So for example, ingredient plus drug strength equals clinical drug components. Nicotine, 1 milligram per milliliter is a clinical drug component. Or nicotine, 1 milligram per milliliter nasal spray, it is a clinical drug. So, and so on and so forth. Let's see how they are connected. And they're connected in a hierarchy you can find in concept answer table. And everything begins with the ingredient. So ingredient is a top level of the hierarchy, is a base of the hierarchy. In our case, it's methotrexate, drug very often used to treat lupus, rheumatoid arthritis, and other autoimmune conditions. It is connected to 2 separate branches. The first one is a clinical drug component, methotrexate 7.5 milligrams. And the second branch is a branch of form, so clinical drug form, methotrexate oral tablet. It's very important to note that these branches are separate and not connected to each other at this level. There is also an intermediate level of clinical dose groups, methotrexate oral products. So this, you can guess that methotrexate oral product collects all the codes for different oral products of methotrexate, like oral capsules, oral tablets. They are all under clinical dose group. But again, branches are separate. And now they merge into a clinical drug. A clinical drug is an ingredient, it's also dose, so drug strength, and a dose form. So it's methotrexate 7.5 milligram oral tablet. If you add brand name to clinical drug, you'll get methotrexate 7.5 milligram oral tablet with some brand name, so branded drug. This is the place when drugs become recognizable, because typically in your pharmacy, you just tell a brand name to the pharmacist. We can also add a brand name to clinical drug component, then we'll get a branded drug component, or to clinical drug form, and we'll get branded drug form, methotrexate oral tablet with some brand. And there are also some very specific, very detailed concept classes. They are less relevant for our example. And this is basically the whole structure of connections. So what's important here, everything is interconnected and everything is connected to an ingredient. Does it make sense? Do you have any questions so far? Good. Now going to our scenarios. We'll walk you through 5 scenarios, starting from the very basic use case with an ingredient, and actually it covers, I don't know, 90% of the use cases, up to the very specific use case, class of drugs with a certain route of administration and everything in between. So, basic use case. You need all the codes, basically you need all the patients treated with methotrexate. In our words, it means that you need all the codes for methotrexate drugs. What you need to do is to choose an ingredient, just ingredient, and all the descendants of it. I will show you an atlas. Okay, let's use the same concept set with a name related to CRP. Okay, and I'm just typing methotrexate here. Now you will see lots of methotrexates. I mean, very specific drugs, sometimes ingredients, but we will be looking for one specific ingredient, which is a standard ingredient. So we can filter it on the left side, my standard concepts. It's already here, but I will show you that you can use concept class filter. Yeah, should be here. Yeah, that's it. Ingredient. So as you can see, there is only one standard ingredient for methotrexate. Yeah.
It's true that in every single situation, that ingredient level will always have the highest DRC because everything maps back to that, right?
Yeah.
By design, there's no situation where you'll find some other representation of methotrexate that has a higher record count that that ingredient can always be synthesized. Because as you showed in that structure of the vocabulary, everything always maps up to that one ingredient level.
Yeah, that's a great comment. Thank you. So I just filtered it by DRC, and you can see it on the screen. So methotrexate oral tablet, some other methotrexates with dose, all the numbers of record count and the DRCs are less than ingredients, so the highest number. So what we do, we just include this one concept with all of the descendants. Oh, sorry, need to go all the way down to the descendants and click Add to concept set. Now we can go back to concept set definition and see that that's it. We have 5,700 concepts related to methotrexate. And believe me, they are all methotrexate drugs. Like, there will be no exceptions. All of them are correct. As I said, that's it. We also have other use case. Let's say you don't need, you want to specify your cohort to only patients treated with the oral methotrexate. So in that case, what you need to do is to choose an ingredient and all of the descendants, like in the scenario 1. Then in included concepts, select the appropriate clinical drug forms plus descendants, and do not forget to remove the ingredient. So in OHDSI, we use clinical drug forms as a proxies for routes. I will show you. So we are back to our concept set. And there we can filter it by clinical drug form. It will show us. Yeah. So you can filter by concept class clinical drug form. You see that there are 10 forms. Some of them are injectable, injectable solution, injectable suspension, or just injection. But some of them are oral, and that's what we are looking for. So click on methotrexate oral capsule, oral solution, suspension, tablet. And this is it. I add them together with descendants to the concept set definition. Now we see that the number of included concepts actually stayed the same. So it's still 5,700 concepts because we did not remove the ingredient. And that's why it's important to not forget to remove the ingredient. So here, remove the ingredient, and you see that the number of concepts just dropped to 532 something concepts. That's it. If you need oral methotrexate or other ingredient with a root, that's how you can do it. But is it really? Because, as I said, we use clinical drug forms as proxies. I don't know why I can click here. No? It's not working. No, it just doesn't react to anything. They already.
So far, are there any questions?
Sorry, I broke the letter.
Did everybody get how to retrieve
Thank you.
all of the drugs with the ingredients? And did everybody get how to retrieve all of the drugs with a certain group? Are we all good? Are we tired? Yeah.
So what can, thank you. What can go wrong except for the presentation? So the thing is, so sometimes drug form does not match the route of administration. And a very common use case is a pediatric formulation. So according to literature, it's up to 80% of pediatric prescriptions are considered off-label. And what are the reasons why they can be considered off-label? You see them here. So it's either dose, indication, or route of administration. So it's a very common problem when routes do not match the forms. And the second use case has been discussed during the OHDSI SOS challenge, is related to bevacizumab. Is a monoclonal antibody used to treat different conditions like cancers. As you can see, it's supposed to be used intravenously, but it can be also used to treat eye condition by injection into an eye. So for these specific use cases, you need to use root concept ID field in drug exposure table. But please be careful because sometimes roots are not populated as they should be. So you need to check how this field is populated. If you're going for some simple use cases and you not expect any eye injection, you can use clinical drug forms as the proxies for roots. And with this, I'll say thank you, and Polina will walk you through other examples.
Hello, everyone. So let's move on to combination drugs. Here we will create the drug concept set that contain combo drugs. In our case, it will be trimethoprim and sulfamethoxazole. And we will select first ingredient and all its descendants. Then within the included concepts, we will search for clinical drug forms because especially clinical drug forms contains combination. At the ingredient level, you will never find combination. So clinical drug forms we should use here. Also, it's possible to use branded drug components in the case if their record count more than 0. So let's go to the atlas. Doesn't react.
Looks like the computer is tired.
Yeah, seems so.
Da-da-da.
Okay, thank you so much. So let's clean up our concept set, if you wouldn't mind. Could I delete it? Okay, good. So let's go to the search tab and type in trimethoprim.
We expect to see a long list of drugs that contain trimethoprim, but we know that we need particularly ingredients. That's why let's sort out and filter to ingredient using class, concept class. Yeah. Yeah, let's sort out by DRC, but it doesn't help us for some reason. Let's select drugs as well. Yeah, vocabulary. But I would like to find ingredient. Oh, lucky me, here we are. So the first row shows us trimethoprim, that is ingredient, standard one, because it's blue color, you see the standard, from RX norm vocabulary. So let's click on the trimethoprim. Oops, go down. Mamma mia. And include descendants, add to the concept set. Then let's go to the concept set. And see, we have 2,000 plus included concepts there. We will go there. And we know that combination drugs should be in clinical drug forms. So that's why we will filter by the clinical drug forms. But before this, we will also include search by name for the second ingredient, sulfamethoxazole. Good. Now, class, clinical drug form. Yes, that's good. Let's also sort them by DRC, descendant record count. And we see the list of 15 terms that contain sulfamethoxazole and trimethoprim. Look carefully through the list. And what is interesting, you may notice that there are some drugs that contain more than 2 ingredients. And depending on the study and your use case, you can exclude them or include them, but in our task, we shouldn't exclude them. So let's remain them here. Select all of them. And carefully go down. Lower, lower, lower. Then include descendants, as we did before, and add to the concept set. We are done. Great. Now let's look at our concept set expression again. What do we have? So we have a good list of combination drugs that contains required ingredients. The only one thing that we should do is remove ingredient. As you remember, we always should remove it if we search especially for combo drugs. So click on trimethoprim, remove selected, and that's it. It's a final version of our concept set for combination drugs. Any questions so far? No, very good. So let's come back to our presentation. Computer doesn't react for some reason. Please, I click, but it. Yeah.
No, I can't get completely out of your. Oh, it's even
Yeah,
me. It doesn't like
work.
me anymore.
It's died.
Today it's the slides. I think it disconnects and come back. Hold on. It's coming back. Yeah.
Oh,
It's
thank you
just the
so much.
connection.
Thank you so much. So let's move forward. The first scenario will be to create a drug code set that contains class of drugs. In our example, it will be tumor necrosis factor inhibitors. But before we proceed, let's recall what is OMOP drug hierarchy. And we know that the core, the heart of the OMOP hierarchy is the ATC, Anatomical Therapeutic Chemical Classification for the drugs. And ATC group drugs under classes and classify them by therapeutic use. It contains fifth level of granularity and five levels of granularity, and fifth level sits on top of the ARCS norm and ARCS norm extension hierarchy, as you see here. And it's represented by a group of drug products that contain information about ingredient, like methotrexate, and also route of administration, systemic. So this fifth level of the ATC has hierarchical relationship to the clinical drug forms. You see this orange arrow, yeah? And clinical drug forms. So we have this hierarchy. And then above the fifth level of ATC, we have 4 levels of classes, drug classes of different granularity. It means the higher we go, the lower granularity becomes. And what is interesting, if you don't know names of ingredients, we can use the ATC class, and ATC will help us to retrieve these ingredients, so we do not need to Google or search for them. And now coming back for our fourth scenario, what we will do? We will find respective ATC class and retrieve all ARCS norm ingredients that belongs to this class. It's very simple. And then we will use ARCS norm ingredients and its descendants. So let's try to switch to the atlas again. Yeah. It's switching my computer, but one second, I will try.
Go back.
Escape doesn't work.
Not escape, just do the up.
Okay.
It's not the computer, it's the connection with the monitor that just goes out of life and then come back. There you go. Here?
Okay, thank you so much. One more scenario I had. So, we're almost done. So, what do we have here? Let's go to the search, first of all. Just, sorry, let me just clean up the concept set and go to the search. Great. And now we will find the tumor necrosis factor alpha. And we see tumor necrosis alpha TNF-A inhibitors at the first place here. And this is particularly what we need, this class. So let's click here at the checkbox, then carefully go down, very carefully. Yes, then include all descendants, don't forget, and add to the new concept set. Very nice. So now we can go to the concept sets and look through the concept set expression. Everything is fine. We have this fourth level of ATC, and now go to included concepts. Currently, there are 2,000 terms included, but we don't need all of them. We need ingredients and their descendants. That's why we just filter here for ingredients. We also can sort them. And now go to ingredients. Lucky me again. So now we see the beautiful list of 5 ingredients that relates to this class. Everything is clear. And let's add them to our concept set. So go down, one list, descendants, including them, add to concept set. Then go to the concept set expression. And what do you think we need to do now? Yeah, remove the ATC. We don't need it anymore. Goodbye, ATC. And remove selected. So we've done. Finally, we have the concept set for the ATC class of tumor necrosis factor alpha. So let's try to come back to the presentation.
Is there really a difference between keeping the class and its descendants the way you had it at the beginning versus presenting that with the ingredients?
No, no. It's just for the beauty of everything. Yeah. Oh, yes.
Also, if the vocabulary team in the future change that relationship, your definition won't change because your definition is picking up the molecule.
Yeah, in the future there you can find more ingredients also in this class. So go further. Fifth, final code set that we are going to create today. This code set will include class of drugs with a certain route of administration. In our case, it will be systemic corticosteroids. And what we will do, very simple, take ATC that we need, systemic corticosteroids or corticosteroids for systemic use, and add with descendants, and then we will remove ingredients. How do you think why we remove ingredients? Any ideas? Ingredients don't contain information about route of administration. That's why are redundant. That's why we should remove them.
What would happen if you increase an ingredient level of the drug when your research question is looking at people exposed to what is that, your specific system? What will happen? Imagine corticosteroid, and imagine you keep corticosteroid in your concept set. What do you think most of the people, what do you think most of these records representing?
Topical, yeah, topical, correct.
Most of the corticosteroids used in the market are actually the supplement. So if you take every single record of that ingredient, you actually would be representing a very different exposure than the research question in the doc, the systemic use. So here you need to be granular, otherwise you will be representing data that actually does not represent the research question.
Yeah, correct. Thank you very much for the addition. And now I'm not in Atlas for some reason. Okay, let's.
Okay, you want to go to Atlas, right? No,
Yeah, it's complicated today.
no, it takes a minute, so it doesn't. See, it just takes a minute. There's nothing magical about what I'm doing, other than it's like.
It certainly looks magical.
Hold on,
Yeah.
we're gonna give it a minute. See, it's just like slow. It's a slow.
Yeah.
Just a quick question on the route of administration detail there. How does that combine with the slide we saw earlier where off-label usage would be misclassified based on route of administration of the RX norm code instead of the route on the drug exposure?
It's basically the same problem. So if you want to be sure, you need to specify a route in the drug exposure table. But it's very often case that the routes are not populated at all.
Yeah.
In that case, you can only rely on forms.
Okay.
And also it's very minor use case. Like among hundreds of sites we've done, there was only one case where it mattered. So usually you're totally fine with regular.
Okay. Thank you.
So coming back to the atlas, just type in corticosteroids for systemic use. I know that it should be formulated in this way, that's why I just write it. And we have various ATC classes with corticosteroids for systemic use, but the most appropriate for us is the first row. So let's include it to our concept set with descendants. Great, now coming back to concept set, we will see 17,000 plus terms related to the corticosteroids for systemic use. But as you remember, we need to remove ingredients because ingredients don't have a route of administration. To do this, we need, oh my God, we need to find appropriate class. Ingredient.
That's a confusing thing about the semantics here. Because it maps to this idea of systemic use, it might look like, oh, that would only include things that are systemic use. But in the relationship mapping, it actually maps ingredient level idea. So it maps
So we are ready to finish this concept set. We need to select all these ingredients, exclude them, and add to the concept set. It's a new approach that we didn't do before. So select, then go down, long list, and here we have the exclude checkbox. Enable, and add to the concept set. And pay attention to the included concepts. So the number reduced because we excluded these ingredients. Let's look to the concept set expression. And here we have excluded ingredients, everything is fine. And one included ATC class code. This is fine. So we have everything that we need for our concept set. Congratulations. And now we again come back to the presentation. Please work. I'm doing this, but really, this notebook doesn't like me. I don't know why. I'm not so bad person.
Oh,
You see?
man, everybody
Yeah.
see my desktop. No!
It's nice.
And now it's stuck. Oh my God. Tick, 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 tick.
Really?
Exposure. And now it's stuck. Whee!
Oh.
Stop.
Yes. Great. Thank you so much. So now we move to exercises, and I invite Anna here to introduce the exercise. Thank you so much.
So we're going to spend the next 30 minutes doing exercises, and that would also be an opportunity for you to ask other unrelated questions. The way we're going to do it is that each team will try to do as many scenarios as possible, starting from the first one till the end. The group that does the most scenarios correctly will get chocolates. Pumpkins, I've heard pumpkins are of interest to people. Pumpkins meaning like Reese's peanut butter. Pumpkins, not real pumpkins. So now we're gonna have 30 minutes, and we will, as usual, have teaching assistants with you helping along the way. All right, so we're gonna wrap up, and we're gonna just cross-check with what you guys have, and I will do it, all of these things again, and we will compare with what you have. So the first exercise was any drug with acetaminophen. So I'm gonna type in acetaminophen, and I'm gonna include all of the drugs with this ingredient, and that will be it. So the first row is ingredient, it is in blue, it's Rx norm. So adding that with the ingredient, with the descendants. I'm adding that to the concept set. So our concept set is just this code with the descendants. How many groups have this? Yay, very nice. So we got through first one. You can throw chocolate at people, sure. We trust you, you know? Oh, very nice. I was thinking you will just throw candies at people, but sure, we can do something like this. So then, the second one is sulfasalazine oral. So our steps is to look for this ingredient, find it, then include it with descendants. In the included concepts, look for the clinical drug forms, include them, and remove the ingredient. So we're adding ingredient. We're adding descendants. I mean, now we haven't candies. So then in the included concepts, we're looking for clinical drug forms because clinical drug forms are the things that carry information about the forms. And we're looking specifically for oral. So this says oral. I want that. This says enema. Doesn't say oral. Enema is rectal. So I'm not including that. This one has oral capsule in the name. That has oral tablet, oral capsule, oral solution, oral suspension, oral tablet, then rectal, rectal, rectal. So I'm adding these, and at the end, I will remove ingredient, and I'm supposed to have 7 clinical drug forms that are oral. Don't throw the candies yet, because we're gonna do that then. Then, how many groups have this? Yay! Sure, yes, throw candy, of course. Go for it. And there is also tricks if Andy or Dima, oh, he ate one, he only... Or we have more. Okay, so the next one. It's a combination drug. So what we said is that we're yet again looking for an ingredient, the first ingredient. We're adding this. I have more chocolate in my room. If somebody wants to go up. So we're adding this ingredient, and then in the included concepts, we will be looking for the second ingredient, which is clavulate, clavulanate. So far we have 5,900 records. So we want to limit it to the clinical drug form because that sits in the top of the hierarchy. So now we have 18, and we can indeed verify that all of them have both of the ingredients in this combo drug, and in fact have no other ingredients by this, but these. So we're gonna add these to the... It expands, yeah. So it's a slightly inconvenient UI, and it just expands. Now, another thing to do here is to look at the branded drug components, and the reason for it is because components live in separate branches than forms. So you just want to make sure that you also captured a second branch. And here we're specifically looking for branded drug components. Why not clinical drug components? Because we don't have combinations for clinical drug components. So hence we're looking at branded. And we're looking for those that have record count more than 0. All of them have zeros, so we don't have to include any of them additionally. Yeah.
Some of them do have descendant record counts though. And some of the branded components have descendant record counts.
Yeah, so they have descendant record counts, but that's because they have branded drugs. And if we were to go back to this, that's a very good question. If we were to go back to this slide with a hierarchy, you would see that we have branded drug form here, branded drug component here, and then they merge together. So this branded drug that is a kit of this thing will already be captured through this thing. And we can also verify it by adding, but if the branded drug components have descendant record counts, you don't care about that because kids are branded drugs and they should be already captured through this branch. Does it make sense? So there is no more things that we want to add. So here it's going to be 19, 18 because we need to remove ingredient.
Now we have chocolate from village.
Yeah, go ahead. So So who got 18? Oh, okay. Some people down. Wow. And then we go to ATC. So we want to include all of the drugs from this class. And at this point, we know nothing about the ingredients. And I don't want to Google them. That's why we're going to use ATC. So we're going to do search. And I saw people looking for interleukin inhibitors and getting, doing like this, interleukin, and then getting a bunch of different things. Like, for example, procedures in SNOMED, and so on and so forth. What we're looking for here is drugs, not procedures. But of course, there are also procedures that mention drugs in their names sometimes. But here specifically, we're looking for drugs. And if we order by descendant record count, the very first row is ATC fourth, is classificational, it is drug. So if we look into this code and edit with the descendants in our concept set, we can then go into the included concepts and retrieve all of the ingredients that live below this ATC term, which will get us, when edit, the full scope of these drugs. So interleukin inhibitors contain, there are 16. Oh, you got something else. So we may check out what you got. Yeah, go ahead.
Why can't you just select the top concept and that's it?
You can. You absolutely can. The one small difference is that relationships between ATC and RX norm is something we built, and internal RX norm relationships is something that is provided by RX norm. So if you want to be like super extra careful, by including ingredients and using the RX norm hierarchy, you have more confidence in the results because there is less potential for the human error. So what you can do, in fact, if you want to be like super pooper comprehensive, you can add both the ingredients and keep the ATC. So then you will have the ATC and the ingredients. And what it means is that in the future, this concept set is less likely to be susceptible to changes or errors because you're both utilizing what we built between ATC and RX norm, and you're utilizing internal RX norm structure by including ingredients and all descendants. And I think there was a question in the back. No? Yeah, so this concept set can be all the ingredients without ATC, or all the or all the ingredients with ATC. In fact, if we include both, we have 1487. If we remove this one, yeah, but I forgot what it was. 87 and 67. So there is a difference, a small difference that is coming from something that lies. Oh, the ATC terms as well, because there are other ATC terms below it. But in principle, including this ATC term and not including shouldn't change anything. All right, and the very last example is corticosteroids. And Paulina showed you how to do it one way, and I'm going to show you how to do it another way. Corticosteroids. So we said that one way is to select corticosteroids, add all of them, and then remove ingredients. This is what Paulina showed you. Another way to do that is kind of do what we did for the first ATC example, which is take all of the ingredients and then look at the forms. So I'm just going to show you another way to do that. So let's say we have we're looking for corticosteroids. There is there are these ATC terms, corticosteroid combinations, corticosteroids and anti-infectives and combinations, other combinations. We're looking for something that just says corticosteroids. And I mean, I know what I'm looking for, but there is this class corticosteroids plane. So we can add that. That thing to the concept set and retrieve the ingredients. So we're kind of repeating what we did for the previous exercise. We're looking at the class, we're then looking at the ingredients, we're gonna add the ingredients and we're gonna filter the forms. So we're looking for ingredients. So there are 35 ingredients here. What we can do is we can add all of them to the concept set. We no longer need this ATC because we retrieved the ingredients that we wanted. And here, because we're looking for corticosteroids for systemic use, we can repeat what we already did for the previous exercises. So we can go from here into the list of included concepts and look for this is a connection pair. And look for systemic forms. So there are two ways to do that, through ATC or through clinical drug forms, the same way we did it previously. So if we filter it to the clinical drug forms, these are already corticosteroids. Now we're looking only for systemic, so we want to limit to the systemic. And if we, I think, and this is the where Atlas gave up because now it says timeout. But basically the procedure here would be to go through this list and identify systemic forms and add them with the descendants. But the list contains 1,500 records and you will need to go through all of them. So for example, this one we will include because it's oral is systemic, topical gel we will not include, and you will go in the same manner through the whole list, and you will filter only the systemic forms, which are either injectable or oral. You will add them to the concept set, and you will have the resulting concept set that is very similar, which will be corticosteroids only with systemic route of administration. And I don't want to do that because I don't want to go through 1,500 of terms and select them manually. And that's why we use ATC the way we showed you before. But I'm just pointing out that you do have a way to also get your class of drugs with a certain route through clinical drug forms. It's just the list now is huge, so you will need to do a lot of work. I didn't actually got to the point where we had, but who finished that last point with the corticosteroids? So now we have 2 tables and a half. Very nice. So you will be getting chocolates from Belarus. We have stickers. We also have stickers. Look at us. And we still have 12 minutes to spare. So what you guys hopefully learned today is to how use vocabularies to create drug code sets, condition code sets, and measurement code sets. Of course, there is much more to it. Because there are all of the edge cases, caveats, and all of the tricky things that you will face when you will actually go and do research with vocabularies. But hopefully this tutorial will give you a basic understanding of what these things are, also where to ask questions, and who to ping if you have problems with these tasks. And if you want to learn more about vocabularies, more of a technical side and more of the guts of vocabularies, you can come to the afternoon session on Thursday. And if you want to learn more about phenotyping, you will come to the morning session on Thursday. And of course, not of course, but the times are flipped. But on Thursday, we're first going to have vocabulary work group, phenotyping work group. It's all on the agenda. And then after the lunch, we will have vocabulary work group. And with that, yeah. Phenotyping morning, vocabulary is afternoon.
It's always been like that. That's just a typo on the slide.
Yeah.
It's always been phenotyping in the morning,
Phenotyping vocabularies. Well, with that, thanks so much for spending your time with us. We do appreciate it a lot. And of course, if you have any questions, comments, concerns, we're welcome that too. If you're looking for certificates, Elise is gonna send you the certificate after the conference. Yeah, we will send the slides to the participants as well.